So now we are talking about that random variable x influencing y, right? There is a relationship between this outcome of the random variable x and y here. What you is the outcome of the random variable y, which is basically the noisy observation. X is ranging from -1 to +1 here, and of course at discrete interval like -0.9, -0.8, like that, right? So you are observing that value of as this x cube plus the noise added with that, and the noise consider here it is Gaussian. It is the Gaussian, right? This is the Gaussian noise, right? Thing is, we have to actually find out this function. That is the thing, right? So we need to find out this function x cube here, which is available. But what is available with you is only that outcome of the random variable y. So how to do that? Start with the function, cost function, c of x comma x cap of y, right? So what is basically, it is the cost function what you are going to as a penalty x cap based on what you are y. So you have some cost function associated with that, and what you are supposed to minimize as an average cell. You need to minimize, that is what this expect is taken, right? So the expectation on the cost, right? X comma x cap of y, cap should come here. Yeah, this is the right thing, right? X cap of y, right? So this one you have to minimize. You need to find out the way how this can be minimized. That is the problem statement, right? So the expectation can be written. Expectation of the function is the function and the corresponding density function associated with that. In this case, we have two random variable x as well as y is available in this random variable. As we are going to minimize as an average sense for all possible values of x and y. So we use here the joint density function. In fact, which is missed here, right? So dx dy. This is what actually you are trying to minimize. Now what we are trying to represent this joint density function as function multiplied with the marginal density function. This is using this base, right? So it is like x, right? So that is written like f of x given y equal to y of x into y of y, right? So this is just like, you know, what we normally do it to even for the density function, right? Like what we normally do is probability of AB. You know, we know that in probability this is probability of AB is probability of A given property being used here, right? But remember that, as you already know, you have to be very careful that I'm not saying this density function as the probability, but this condition holds true for the density function also. That is what I'm trying to say, right? It is not just a density function. Probability is with the density function for the continuous case, not like that, right? So as you know, in this case, this cost function we have written as this, and this joint density function is written as the product of the conditional density function into this marginal density function, right? So now what we do is it is equally writing, and we can write in terms of expectation like this. It is like, you are taking this expectation of, right, the cost function. This is what we call this conditional expectation, right? So I'll write like this. Before that, I just give you the hint about how that is a trick involved in getting that. Suppose that if I want to take expectation of x, I can do one thing, right? I can take expectation y equal to y and take the expectation over, right? This is basically the expectation of x. This is a trick we are going to use. It is something like, if I want to know average of all the marks, we can actually calculate average of the marks in each class. Y indicate the class number. In each class, we can actually find out this average of marks and then take averaging over average to know about the marks, right? So this trick only we are going to use. In fact, mathematically also it is true. If I expand this expression, you will get this expectation of x happen to be expectation of x given y equal to y, and take the expectation of y, and that is what given here. So this expectation is not that, there is a mistake in this. So you are taking expectation y, and but you are taking what is called this condition, right? You are taking this conditional okay, I'm sorry, see, okay, right, this expectation is for the conditional expectation, and then you are y here, right? This is the function, and then you are taking y equal to y, the value, and then taking expectation over y. So let me write it clearly here. What I'm trying to say here is, you are taking this expectation over the function, whatever the cost function involved. X cap of y is the cost function involved, right? Given y equal to y, fine, right? You are taking this conditional expectation. This is called this conditional expectation, and then you are taking this expectation over y. I hope this is clear. You are taking the conditional expectation and taking that expectation over y, and that will become automatically, that is exactly expectation, the cost function, right? So this is okay. This trick is here, right? So what we are doing is, we are starting from the cost function in assigning x cap of y, which is the basically the estimation, right, with original value. This is the original value. X cap of y, observation of y. When you do this assignment, you are supposed to give some penalty in it, because if there is some error in it, and this cost function will give that penalty, right? If there is no error and this cost function is actually becoming 0, like that only you have to form a cost function, right? So you are trying to minimize this as an average sense. So while creating this expectation, you are actually now doing expectation of the conditional case, right? Expectation is what we call it as conditional expectation, and you are taking expectation over y, right? So now we are interested in minimizing this. We are interested in minimizing this. That is a task. The task is to minimize this function. I hope this is clear to you. So there is one question here. Why is the cost function being multiplied with probability density function? Error. Oh, okay. That is the, I don't, you are aware of this expectation of x, right? If I want to find out this expectation of x, we have to do this here, that corresponding density function into dx. This is the definition for finding out this expectation of x, right? So this is if I want to find out mean, we actually need the density function to find out that. and that is the reason I want to find this expectation of this cost function. Even not only that random variable, it could be the function also. We have to write this function here, and then you have to write the corresponding density function. Then only as an average you will get, right? The definition for this expectation itself is this only, right? You can actually check the basic probability theory, right? By definition, if I want to take the expectation of the random variable x, right? So you have to go for x and then for the density function dx, right? So this is the way how we compute the expectation, and that is the reason why it is given like this. You can actually see some basics of probability that is important for this course. It is not very difficult, right? So now what we are going to do is, instead of taking the expectation of this cost function, right, what we are having here, we are writing the expression use this trick. What is the trick? Intuitively I'm writing now, expectation of x can be written as expectation of x given y equal to y, and take the expectation over y. And I already told that the intuition behind this one is, if I want to find this average of average marks scored by 10 classes, you can actually take average of marks for the individual class. Here this y indicates this class number. For every class you can actually find out this average and take the average over the class. So you will get this average over the marks in this, right? So that is the way how we can actually calculate this trick. This is the trick we are using. We are taking this conditional expectation and then taking over y, right? So that not exactly written here in this. So while calculating this expectation of this cost, we are writing expectation of that one, that cost function, whatever it is, given y equal to y, we are finding, right? And then taking that expectation y here. Okay, so right, so we are taking this, you see that, so I am writing clear manner like this. This is the expectation of the cap of y, right? And then on y, and then taking this expectation over y, so you get this expectation of that. This is this you can compare with whatever I told. I mean, anyhow, one more time I will write that one. If I want to find out this expectation of x, the trick is given y equal to y, right? And then take expectation over y. So that is the thing. That is the exact trick. Instead of x now, instead of x, you are having now function. Some function. It could be the function of, in this case, the function is c, right? Any function we can actually think of, right? Even it could be the function of x comma y also, right? So we are actually, in place of this as x, we are using this function. That is the thing. The function in this case is c of x comma x cap of y. Okay, fine. Now we are interested in minimizing this. That is the major thing, right? So see, and one more point I just want to mention here, even if you are not very clear in all the steps, doesn't matter, right? We can actually recollect all those things, but what you have to understand is, what is that MMSE, right? That is what I'm trying to prove, right? We already know conditional mean, conditional median, and conditional variance. Why that is coming, right? So that is what I'm trying to explain you, right? So now x cap of y. Okay, I just, this is the doubt what you are having. X cap of y. Basically, the original value is x. Okay, original value, because you remember that you are observing y and you would like to know what is the value of x. That is the case now. I mean, this problem, yeah, this problem is you are estimating x. The problem in this one is estimating x. Okay, I'll start like this, estimating x. You are interested on estimating x based on the observation, based on the observation of y. Okay, So the original value is x, and you are estimating that x as x cap of y. Now, I hope now you are getting right. The original value is x, and you have this x cap of y is the estimate of that. So when I am assigning, see, for example, let us say this original value is 0.5 and your x cap of y, right? So you are estimating that value as 0.47, something like that. You have some error in it, right? So there is some error in it. So that error, we are giving something like a penalty. This is what we call it as a cost function, right? So we are giving some cost function that is having the value of 0.5, and then you have this 0.4. To assigning, I mean, you are actually estimating that 0.5 as 0.47. So there is some error in it. Suppose that if I'm estimating this value as 0.5 itself, exact value, then the cost function is going to be 0, right? So this is what the cost function involved in it, right? So you are trying to minimize this cost function. So that is what the case here. So you are trying to minimize that, and for every values of y, we are trying to minimize this cost function as an average sense, and taking the expectation over all possible values of y. So this is a trick what I told little earlier, right? So this is what done. So to minimize this, what actually we can do is we can minimize what is there in the inner part. For every values of whatever you observe, right? So it is a penalty. Let me put it as C. For every values of y is what you do in the experiment, right? You are trying to minimize this cost function as an average sense. If you are trying to minimize this one for every values of y, then automatically get maximized, right? So this will come here. Okay, so it is like that. C is the cost function. Yeah, what he has written? Same for the output y. First, we may try to find the relationship between y and x and y. The cost function will be y minus y hat, which is to minimize. Y hat is estimated output, and y is the actual output. Do it for the output. See, don't get confused now with input and output. I don't know, that is the reason why you are getting confused. Don't worry about input and output as of now. As far as this slide is considered, don't get confused with this input and output what we had it at the earlier slide. So everything is going to get it related later on, right? So don't get confused with that. So this particular slide focus on, you understand the point. The problem statement is very clear. You are trying to estimate x. That is the thing. X is the thing which is actually you are trying to estimate, right? Whether it is the input or output doesn't matter. We have one random variable x which you are trying, and you are estimating. I mean, x is the one which you are trying to estimate, right? And you are trying to estimate based on the observation of y, and that is the reason we have what is called x cap of y, right? So now, yeah, is this the inner expectation over the range x? It say that inner expectation, we are fixing out what the is going to be that function of x, because you are anyhow. But remember that while finding this cost function, you are actually fixing this y. That is the meaning of it, right? What you are saying is right. Okay, what you are saying is right. Now, instead of doing this task as the conform, what we are trying to do is we are trying to minimize what is there inside, this term for every values of y. That I have written here. This is equivalent to minimizing this for every values of y. If I do that, then your problem gets solved. So I repeat the problem once again, right? So those who have joined also, let me put a simple summary on what I repeat once again this problem. Problem is you are estimate the x. X is the one which you are interested on based on the observation of y. That is the problem. You are observing y now. You are observing y based on that. You are trying to estimate this x. X is the estimate of that. X is the one which you are trying to, I mean, original, and x cap of y is the one which actually you are trying to estimate based on the observation of y. I hope this is clear to you, right? Now we are going to find out, for finding out that we are actually creating something called the cost function. What is that cost function? It is a penalty, right? It is a penalty for doing that wrong estimation. Let us say that original value is 5 and then you are estimating that one as what? 4.9, right? So this 4.9 is the estimate of x only, but you are estimating that value of x. Both are, this is x here and this is going to be your x cap of y, right? You are estimating the value of x based on the observation of y, and that is what you are getting it as a 5.9, right? So that way you have to think, right? So you have some penalty in it. We are trying to minimize this. We have to do this one for all possible combinations of x. Which one we wanted to minimize. And we are actually why do we need to estimate based on y when we know the exact value of x? I don't know the okay. How will you know the original value of x? Okay. Arun, which dip?
Yes, sir.
Yeah, Pramod.
Sir, I'm from Triple E.
Triple E. Okay. See, you have to this original value of x is known it on the theory. You understand the point, right? So it is something like this. I'll put the motivation behind this one in a different way. Then you can understand, right? So that's what I have shown the previous slide, but still if you are not able to understand, I think I can give you the motivation behind it. Then I will go for that math involved in it. It is the straightforward. I don't know whether you attended the previous class or not, right? So anyhow, what I'm trying to say here is it is just reversed. In the earlier case and this case is getting reversed. That is the problem, right? So you have x, right? Now it is getting corrupted. Say for example, you have that noise, right? You have, okay, in the early case, what I mean in this case, right? So you are trying to find out what is this value. That is what the case, right? So you wanted to know what is the value of x based on of y. Okay, you understood the point, no? So the x is not actually known to you, but I know. I mean, I know in the sense for theoretical development, right? So we know that the original value is going to be x because we have some model like this: y equal to x plus noise, right? Noise is, say, for example, Gaussian distribution, right? It is like that. It is Gaussian distribution, right? And x state, say for example, minus, right? So it will take one of this value, right? So and you are getting some observation about this y, right? So now the question is based on the observation of y, you are observing based on this observation of y, you would like to know what could be the value of x. That is the problem. But this development, while doing this theory development, we have to assume that x is known for some value of x. It is you are getting this observation y, and what is that? Because it is a random variable, x takes some value. Variable. We don't know actual value of x, but we know the characteristics of the random variable x. right? So once you know the characteristics of the random variable x, based on this observation of y, what we estimate the value of this x, right? So that is the problem now. I hope, are you getting now? Pramod or Vaishnav? Yeah,
Yes,
so
sir.
this is
Thank you,
the
sir.
motivation, right? This is what I'm trying to say, right? So now you are trying to estimate x as x cap of y, because you are observing only y, and what is the of x, and hence it is called y, right? So now coming back to this original track, we are trying to increase this while assigning the value, right? This is the original value x, and this is the x cap of y, right? So a typical outcome of the random variable x is x here, right? And this is the one which we are trying to estimate. Typical case. In that case, we have some cost function associated with assigning x as, I'm sorry, x cap of y as x. You are estimating x as what? X cap of y. So we have some cost function associated with that. And this is the cost function here, right? We are trying to minimize this one in average sense. And that is the reason we are taking this expectation. While you take expectation, you need to multiply with what? The density function. Of course, the double integral should come here. So then dx dy is there. And then we are trying to write this one in this form, right? We are taking this expectation, conditional expectation, and taking the expectation over all values of y. And that is what we are doing here. I already told the trick is very simple. The trick is, if I want to take some function g of x comma y, that function, say for example, this is one example I'm building. If I want to do that, we can do this one by fixing y, and then the expectation over y. Understood? So you can actually do that. So you, whatever the function you are having here, you can take this expectation by fixing one random variable and take the expectation over that random variable. This is the trick, and this trick is actually exploited here. You are taking this expectation of this function, that cost function, given y equal to y, and then taking this expectation over what? All values of y, and that's what you are doing. But now, instead of, see, our requirement is to minimize this, right? To do that, we are trying to minimize this inner part. For every values of y, if I try to minimize this, right? For every values of y, if I try to minimize this is actually there in the inner part, right? So for every values of y, if I do that, then automatically we get this total expectation as an average, since we got what? Minimized, right? So that is the task now. Now we are actually narrow down the problem statement, right? So even though we started with minimizing this one, only this. If I do so, if I try to minimize this alone, that is enough for us. If I, for every values of y, if I try to minimize this, the conditional expectation one for every values of y, you are through. And depends upon the cost function, we are going to have different estimation. That's what last class we discussed about three different ways of here the squared error is what actually you are given as a cost function. That is one of the way, right? X minus x cap of y, the whole square. I am trying to minimize this as an average sense, right? We have to take this expectation. And what could be the another? That another could be the absolute, right? Something like that, no? Instead of minimizing this squared error, I can even go for what? The absolute error. This can also be there, right? I can reduce this error. So the cost function, you have your own choice, and depends upon what cost function you are using, you get different estimation value. That is the thing, right? So in this case, this particular case, we are using one. You can see that x minus x cap of y, the whole square. That is the thing we are using here. Actually, are interested in x cap of y, we can as a variable, and so what we do, we differentiate this expression I to 0 and solve for that. If I do that, you get x minus x kappa phi the whole square, right? So it is integral minus infinity plus infinity x phi the whole square. Given y
Sir,
equal to
some
1.
people are waiting.
I'm not seeing anyone in that. Right? As we are having this condition for what is called the conditional density function equal to y of x into dx. Okay. I could use this is a function, and then you have to, as in this case it is a conditional expectation, because you are taking this expectation given y equal to y, we are actually going for this conditional density function, right? This is what we need to do. And then now it is very straightforward. This one we are trying to minimize, and now the unknown thing is actually this x kappa of y. I already told this x kappa of y is the unknown one, so you are differentiating actually with respect to this x kappa of y, right? So you are getting 2 times x minus x kappa of y, and this density function as such it is coming dx equal to 0, and then you are expanding this, right, x into the density function in the right hand side, and of course 2 is coming in this also. Yes, we can remove, right, because that is equated to 0 only. So here this 2 will not come. Now it is integral minus infinity plus infinity x minus x kappa of y. If I take this term, right, x and fx given y equal to y of x in the right hand side, and left side we have written x kappa of y f. So what you see in the right hand side is what we call it as the conditional mean. This is exactly what is called. This is called the conditional mean. This is basically the expectation of x given y equal to y, right? So this is what we are doing. Okay. In this case, what is it? You are actually fixing y. We are taking only integral for x only, because you are fixing this y. We are fixing y and we are doing this, right? Don't get confused, right? Even though we are using this density function, you are fixing that value of y given y equal to y. That is the meaning of it, and the whole integration is with reference to x only. But what is at left hand side? Left hand side, this x kappa of y, we are doing that. We wanted to find out this value of x kappa of y. The area under the density function, the conditional density function, is actually 1. Take this x kappa of y outside, you actually get this integral, the complete integral over the conditional density function, right? Fx given y equal to y of x dx. Okay. If this value is actually density function is actually going to be the simply x kappa, is simply x kappa of MMSC. We need as a solution of MMSC. So that is going to be the conditional mean, right? So this is equal to integral minus infinity to plus infinity, x fx given y equal to y of x into what? Dx, right? So this is the conditional mean, right? So I hope this is clear to you, but this involves the probability theory, where you must know the definition for the expectation and all, right? We are differentiating this equation. Okay. We are differentiating this. This is the equation we are differentiating with two. I'm sorry. We are differentiating this. Okay. And that is written expanded here. This is the same. Okay. Right. So what you see here is expectation of x minus x cap of y the whole square given y equal to y. If I do this expansion, this is the way how we have to write. And then if I do this differentiation, after differentiation, you will get this expression. And you are doing differentiation with respect to x cap of y, right? Cap of y, right? I am not getting that question, Vikesh, what he has written.
Yeah, sir, are you able to hear me now?
Yeah, tell me.
Sir, so let's say initially we have 0.5 as the original value of x and x hat of y is 0.47. So we do this calculation to, like, what is the final purpose, sir? Here we are getting x cap of y MMSE. This value will be the input
I
value of
understand.
x cap of y or something?
No. I will tell you.
Okay.
So you
Okay.
understand that
Okay, sir.
x cap of readily available, right? X cap of y is not readily available. You have to understand how to get the proper value of this x cap of y. How to get this? That is the question. So the question is, what is the value of this x cap of y, right? That minimizes this function, this objective function. What is the value of x cap of y? That 0.5 and all to make you understand what is meant by this cost function. At the beginning, we do this variable. It can take any value, right? Within that, having some density function. We are writing this cost function. Suppose that is what the idea, right? Suppose the original value is x, and suppose that you are estimating that as what? X cap of y based on the observation of y. Suppose there is nothing like we have the actual value of x and we have that actual value of what? X cap of y, not like that. Suppose if you are estimating x as x cap of y, suppose, right? Then the cost involved in doing this assignment or doing this estimation is this expectation. And then we are trying to minimize this one because we are doing this assignment, we are doing this estimation, so there is some error in it, and that one we are trying to minimize, right? We are interested in knowing about what to be the better way to find out this x cap of y that minimizes this the whole function. That is what the problem is, right? The problem suppose that is this problem. If I have the original outcome as x, and suppose that you are assigning it as x cap of y, it doesn't mean that you are going to assign like this. Suppose you are assigning like this, there is a error involved in it, right? And that error you are structuring as a problem here, right? And then what could be the better way? We are interested in minimizing that error involved in assigning x as x cap of y, right? We are trying to minimize this. So our requirement is to find out this x cap of y, right? So we are actually formatting this problem, and this unknown to 0 and this position as conditional expectation. What actually you are getting finally, the expectation, I mean x cap of y is the one you are, right? So this is a better choice we are saying, right? So if I have some other value of x cap of y, this function will not get minimized. That of it. This will get minimized. But I mean, suppose that if my cost function is this one, if I choose this x cap of y is this, then your cost function will get minimized. That is, are you getting now? You can ask me again if you not getting, no problem.
Okay.
Vikesh, Vikesh.
Vikash.
Vikash, yeah, Vikash.
Yes, sir.
Are you
Now
getting
it's
which
clear, sir.
department you are? Yeah, yeah. See, actually, this is the
I
starting class, right? So slowly we will understand. Anyhow, this is not directly related with this pattern recognition course. You must know these basics, right? So because this is a yardstick. When it comes to this machine learning pattern recognition thing, right? We go for the training technique. We go for training and we do that. But we need something like the reference one, which is what is a classical method, right? So to attempt to do this type of regression problem, right? So then only we can actually come this if it's with the statistical way, right? So that is the main goal. This derivation, as far as this course is considered, is not for those who are interested in knowing this derivation can go through that, right? But what is more important as far as course where this is important, right? So, but as far as this proof is not needed for you, there are other proofs, of course, available. Particular proof is not actually needed for this as a part of the, to make clear, to understand to the depth, right? So what is that we are doing, right? So let me give you a simple summary of what we have. Still better. It is this is what the problem is, right? It is like, I mean, it is something like this: x plus noise, right? You have the outcome of, and what you observe is the outcome of the random variable y. You understand that x can take any value. I mean, we can, let us say that x is taking that value like -1 to +1. It is all defined. It is well defined, the possible values that x can take, right? So these are all the way how we can define the outcome. Say, let us say we have this probability of x equal to 1 is something like p, and then probability of x equal to 1, it is we have a description. The simple two choice, but you can have, then what you observe is not just 1 or -1. You are getting the observation y, right? Is a noisy one. Like you observe that one as 1. Observing it is, sometimes you may get the observation as 1.9, right? So now it is like that. So based on what you get, based on what you observe, you would like to know what could be the value of x. That is the problem statement. Now you are trying to estimate the value of x given y. You are trying to estimate the value of x given y, right? So it is like x cap, right? That is the problem, right? So you are trying to do that, right? So we are assigning the cost function by doing this assignment, right? And then we are trying to minimize, and the solution happened to be the solution. What does it mean? It means that you are having the density function of fx given y equal to y. For a given y, you have what is called the density function. something like that, right? So this is the density function given y equal to y. You are actually fixing this y equal to y, and then you are trying to find out the density function given y equal to y. It is a function of x because you are fixing y. It is a function of x, right? And then you are trying to find out what is the mean of this random variable x. So that is actually computed as what? Integral, right? X into the density function fx given y equal to y of x exactly what we call it as MMSC, minimum mean square error, because the cost function what we have chosen here is x minus x cap the whole square. Suppose if I use some other function, it will end up with a different solution, right? For example, right? So this one, not going to give more details on the proof, right? So what I'm telling here is you have what is called this absolute difference, x minus x cap of y. So in the earlier case, we had x minus x cap of y the whole square. That is what we try to minimize. That is the cost function we had. Now we have what is called x minus x cap of y, right? This one we have chosen in this. The procedure is the same. You have to again differentiate, right? X cap of y, right? This is the function. Case here. So this is, and then if I differentiate this one with respect to x, if I saw what you get the solution as MMAE. It is at MMAE. So what does that mean? So in the earlier case, we had a density function, right? So in this case, what is called, the conditional median is coming into picture. It is basically the area all the way from minus infinity to, we have like x cap of y MMAE. So MMAE is just a notation, the solution, right? So minimum mean absolute error estimation, and then we have here this area. This area this function is basically, what is function? This function is basically the conditional density function fx given y equal to y of x. You are fixing y and you are trying to find out what is that function of x. Location where this area and this area is the same, and that solution is coming if the cost function is the absolute x minus x cap of y, that absolute value you are trying to minimize, right? In this case, right? So that is ending up with what is called MMAE, right? So what I'm trying to say here is this is only the basics before going for the actual class. Actual class is we go for the regression model, linear regression model. We concentrate on this parametric approach and all, right? But this is something like this yardstick to compare, right? You must know this thing, right? What you must know as far as this course is considered is, right, if I have the random variable x, right, and you and they are getting influenced. We have a random variable x and that is influencing y. You are observing y. You are observing y. That is the problem. If that is the case, we are trying to estimate x as x. How to do that? How to do that? That is done by using the conditional density function. Which density function? which is basically what is called as posterior density function. Last class we discussed about this prior, posterior and likelihood, and this is what we called as this posterior density function. Remember that depends upon what you estimate, you have to have that corresponding function here. In this case, you are trying to estimate x, and equal to y of x is what we call it as the posterior density function. Suppose if I am trying to estimate y, it could be the other way around. Fy given x equal to x, right? But as far as this is case is considered, you are trying to estimate x based on the observation of y, and hence this is going to be your posterior density function. Known how to get a solution. There are three ways to get a solution. One is the conditional mean. That is actually the solution for MMSE. So that is the conditional mean. Conditional mean. That becomes conditional median, right? This is conditional. One more, right? And you have to understand that MMSE is actually the solution if the cost. That is what you must know. As far as this course is concerned, what you must know is this. And then we have finally what is called this map. Next slide, we'll discuss that one. Before that, so MMSE, what is that cost function? This is the cost function, okay? So this is what you must know. This part alone. This is the cost function for MMSE. And consider this is the cost function, right? X minus x cap of y, that absolute difference is going to be your cost function. So what about this map? What is that cost function for that? Is now this cost function for this one, when you are assigning.
Excuse me, sir. Sir,
Yeah.
could you please explain how MMAE and median are related?
Definition. By definition, what we really mean by that is we have a conditional density function right here, right? So the
Yes, sir, correct.
about that, right? So what is more important is this density function here. Okay, I'll put it like this. We are trying to find out what is it mean in case of MMSE. In case of MMAE, we are trying to find out this location. We are calling this as a median. We are trying to see median. How do you find usually? If I have an outcome of the random variable in case of discrete, right? What you do? You arrange them in the order and you will try to pick up the middle one, right? So that is what exactly we are doing in this, right? We are trying to find out the middle one here, right? So this is
So that the areas on the left and right are equal.
right? And the density function still it is going to be the posterior density function, the same.
Okay.
MMSE, MMAE, and then map. In all the case, you are going to use only this posterior density function, fx given y equal to y only, right? In one case, you are trying to find out mean. Another case, you are trying to find out the location where this left area is exactly equal to the right area, right? Which we call it as MMAE, right? And we have the third one. So forget about what is there in the bottom, right? You just see this part alone now. Don't see the other thing, right? So here this cost function is the original value is x, and then your estimation is x cap of y here, right? The cost function we are fixing it as what is called 1 by. If this x minus x cap of y, if it is greater than delta by 2, what does it mean? The error original value is x, and then your estimated value is x cap of y, and this this absolute difference, right? If it is greater than some quantity, that quantity is given as delta by 2 here. If it is greater than delta by 2, you are not happy. That is the meaning of it, right? So if that is greater than delta by 2, you are giving some penalty, and that penalty is 1 by delta here. It is purposefully chosen, right? It's based on this cost function, right? You are assigning some constant as the penalty here, which is 1 by delta, right? If this difference in the cost, I mean the difference in the original and the estimated one, if it is greater than or equal to delta by 2, if it cost function, it is simply 0. That is the meaning of it. So if this x minus x cap of y, if it is greater than delta by 2, right, your cost function value is 1 by delta, right? If x minus x cap of y, if it is less than delta by 2, right, then your cost function is 0. What does it mean? It is okay. You are saying that quantity, you are saying that, I mean, the right, so it's like, for example, if the original value is 1 and you are 9 and some error 0.01, right, so you are saying that 0.0 is fine. Estimating 1 as 0.99, the cost function involved is 0 only. I'm saying that the cost function involved in assigning the original value is 1 and you are estimating it as a 0.99, and I'm saying this difference, which is less than a particular quantity, if it is there, then the cost function for me is simply 0. You understood the point? I hope this one is clear to you. Are you getting this? Right? So if the difference in the, yeah, yes.
So we have another class at 3. So can you continue?
Okay,
And
we'll stop
till
here.
next class?
Right, we'll stop here. But what you must know, next class, I'm not going to discuss these 3 things again. Right, so we are going for this linear regression the next class. Right, what you must know is the corresponding objective function in all the 3 map. What is that objective function? In this map, again, we are going for again the conditional density function, and we are looking for the peak in it, right? So that is what the thing in the solution for this one is the conditional density function. Again, you have to go for a peak location for what values of, right, function of x, right, something like this, right? And the density function here, what we are considering here is posterior density function. In this case, you are actually trying to locate the location where you are getting this peak. This is what we cost function. The solution what we get is this, right? If time permits, in the next class we will try to do this workout also. So for some students, they may be interested in knowing that solution, right? So we'll go for that workout also. We'll start with MMAE in the next class, right? So that you can understand it better. Before coming to the next class, just go through that basic expectations and all, right? So that will be easier for you to understand. We'll wind up now. Is that okay? Okay.